All right, hi everyone. I'm Lalit from BMI Research, and today I'm happy to be up here sharing some advice that I hope will help you, new PhD students, with your journey in systems research. So there's no shortage of very good high-level advice out there on how to go about doing a PhD, right? There's a lot of good advice on things like problem selection, managing your advisor, reading research papers and how to interpret them and so forth. In this talk, we're going to focus on what's called low-level advice, which is advice that will hopefully help you with the daily battles you're fighting on the ground. And in systems research, this usually means problems around building a complex system, running experiments, and doing all of that under the pressure of a looming deadline, where things start to really get chaotic. And hopefully you'll find this advice to be actionable so that you should be able to go back to your projects, apply this advice, and that'll hopefully help you ameliorate some of the chaos that happens as you get closer to a deadline, right? So with that, let's get started. So as a systems researcher, you're going to have ideas. And when you have an idea, your goal is to build a prototype that implements, say, the hypothesis that you have and run some experiments that validate that particular hypothesis. And depending on the outcome of the experiment, you refine your idea or you realize, okay, this, maybe I wasn't on to something, and you fail fast and you move on. So your goal throughout this process is to make sure that you can prototype and run experiments in a way that lets you gather continuous incremental feedback about your idea. So what you really should not do is have an idea and then spend like say a year or two building a prototype and then run your first experiment and realize, oops, I've completely missed the mark. So don't do that. Make sure that the cycle that I'm showing you here is something that you can do at very low time scales. Make some changes to your prototype, run experiments, refine your idea, and iterate. And in this talk, we're going to see how you can prototype and run experiments in a way that supports this goal. All right. So first, we're going to focus on the prototyping side of things. So when you're building a prototype, what that means is you're building a system. Your system will take some input and will produce some output, right? Very high level picture of a system here. Now, any complex system is usually going to have multiple components that it that needs to somehow work together in order to translate these inputs into the outputs that you want. Now, the absolute wrong way to go about building something in order to support our sort of fast iterative style of doing research is to go about it in sequence like this, right? Where you painstakingly gather all the inputs that you want to support, write the first layer of your system, and then the second, and the third, and the fourth, and so on until you finally are at this point where you're ready to do this grand unveiling where you finally see your system work end to end. And then you run it and realize you've completely missed the mark, right? So don't do that. Instead, what we're going to follow is the principle of building systems end to end as soon as possible. And in the industry, this is kind of known in one particular book, the Pragmatic Programmer book by the tracer bullet methodology. The idea is that you start with the simplest possible input that you want your system to support, and then you trace a line through the code, taking as many shortcuts as you need in order to produce the expected output for that particular input. All right. But what you've done here now is that you have an end-to-end working version of your system ready. It doesn't do much. It only works for this one particular input, but it runs end-to-end and you see it work. Now you can start from here and you can slowly add more and more complexity. You add more kinds of inputs and then you fill in the blanks in your code and you follow this process all the way until at some point you have a working system that you can then run. But the catch is that at every step along the way, you're basically getting incremental feedback about whether your idea makes sense or not. And you can see that always because your system is working end to end at every step, right? Now, this is a bit abstract, so I'll try to make this a bit more concrete with an actual example. So I'm going to mention some work that we did, we presented at OSDI last month. So this is a system called DCM or Declarative Cluster Managers. And our observation in that paper was that a lot of cluster management code in the industry, like this is the kind of the kind of code that keeps your data centers running. Right? Think of your schedulers, your load balancers, your resource management logic, and so on. We find that such cluster management code is often written, is kind of reinvented over and over again. And developers tend to craft ad hoc heuristics to solve these problems in many different settings. And these heuristics usually come with a lot of problems, right? Like we found that they're hard to scale, they're hard to add features to, they're not very flexible, they don't compute good decisions. And so we hypothesized that it might be possible, instead of writing these things by hand each time, to specify their behavior at a high level using like a declarative language like SQL, and have a compiler generate a blob of code that you can run in place of these heuristics. And this generated code under the covers would use something like a constraint solver in order to do the necessary computation. So this was the idea that we had. But when we started this project, we had like, there were just too many unknowns here. Like we had no idea whether SQL was an expressive enough language to express all the behaviors that people are writing heuristics for today. We had no idea whether it was possible to write a compiler that can take something like SQL and produce an executable batch of code that you can, run at fast timescales. And whether this generated code would be able to effectively interface with the constraint solver and meet the demands of scale that these actual systems have. Like we had no idea about any of these things, right? So the dumb thing to do here would have been to actually, think of all the SQL we wanted to write a good compiler for it, make sure that it generates good code, and make sure that it's working effectively with the constraint solver, take this and then start to integrate it in different systems and then learn whether it's effective or not. Doing this would have taken too much time, and it would have been too risky, right? We wouldn't know where we would be headed to trying something out like this. So instead, what we did is we picked one use case. We picked a simple use case. This was a transactional data store that we know runs in one of our products. And we took its cluster management code and we expressed that using SQL. And we wrote the simplest possible compiler that we could to support only that SQL that was related to this particular system. And in doing so, we really mocked large parts of the compiler, right? We took as many shortcuts as we could. And eventually what the compiler produced was only partly generated code. And we filled in a lot of the hard bits by hand. And we used a constraint solver that was quite easy to use, but it wasn't that performant. But it meant that we could easily write this code that we needed to by hand, right? And note that all of this is only meant to support the SQL to represent the cluster management logic in this one particular system. But even before we had a working compiler, we actually had a working end-to-end demo within a couple of weeks in an actual system, right? And we learned a lot doing that, and we got a lot of the confirmation that we needed, that our idea actually makes sense. And we could show this demo to our colleagues and engineers within our company, and the feedback helped us get the necessary confidence to double down on this idea. And then over time, we integrated with more use cases, we filled in more gaps in the compiler as we went along. We eventually changed the constraint solver to be something that was harder to use, but much more effective. And slowly we had a good system that we were happy to write a paper about, right? So the moral of the story is always prototype end to end so that you see the system work in front of you early on, and then iterate on that, right? And that's the best way to get feedback on whether your idea makes sense or not. So that was it for the end-to-end prototyping part. Now I'll talk a little bit about testing your prototypes. Now, the main thing I want to convey here is to make sure that you test for correctness before you run experiments. So the goal of your experiment is to validate test a certain research hypothesis, right? And here you're usually looking for complex things like performance metrics and the behavior of systems, which are all hard enough as it is. Don't compound that difficulty by also trying to debug for correctness at the same time, right? So test for correctness while you're developing a prototype, not when you're running experiments. So here are some tips to help you with the testing side of things. So make sure you have a suite of tests that you run on every build and every commit. Every language has its own umpteen frameworks to do testing. Pick one. Right? For example, in Java, you have JUnit. In Go, you have Go test and whatnot. Now, besides test, it's also helpful to use any automated tooling available in a particular language's ecosystem to harden your code. So all of my Java projects from day one, I configure them to use these static analyzers like Spotbugs and Google Error Prone, which flag errors that are not compilation bugs or compilation errors, but for example, bad programming patterns where I'm using a library the wrong way, like a very known wrong way, right? Like, so use any automation available to stop you from making bugs before you hit your experiments. And one way to force yourself to make sure that you're always running your tests and this automated tools is to use what's called continuous integration. There are a lot of free alternatives that you can use. I've listed some of them here. There's Travis, which is definitely free for public open source projects. And what these tools do once you set them up is that they listen for commits that you make to your repository. And whenever it sees a new commit, it'll check out the code and it'll run your build and your tests and so on, right? And if something fails, it'll complain. And if things pass, you get this cute check mark on your commits. Now, the reason to have all of this in an automated way is to slow down the rate at which you're introducing bugs into your system. And this is especially important when you're working on a team and you're getting close to a deadline and you want to be sure that everyone's not trampling on each other. Right? So automated tests and having continuous integration slows down the rate at which you introduce bugs. And this helps you keep your sanity when you're under a lot of pressure. And don't forget, like when you find a new bug, let's say by running experiment, make sure you can reproduce that bug by adding a new test case and add that test case to your test suite so that it's now you're making sure that no one's going to introduce that bug again in the future, right? And keep it running with your build every time. So that's it for the testing part and the prototype side of the advice. Now I'm going to focus a little bit on the experiments and how to be efficient about running experiments. So again, the goal is have the short cycle and make sure that every change in your prototype is backed by experiments that let you, inform you about what changes you have to make next. So the first advice with your experiments is to make sure that you set them up as early as possible. It really goes without saying that if you want to keep that cycle short, you have to have the experiment infrastructure early on, right? And this is especially important for projects where you really, defining a problem relative to the state of the art in some sense. So in these cases, you really have to have the experiment infrastructure ready even before you build anything. And the reason to do this is that you should really gather that kind of experimental data to understand the problem and the state of the art before you set out to do something, right? And in the process, this actually lets you validate your assumptions. Sometimes just reading papers can give you a very skewed impression of what the actual problems are. So get your hands dirty, run some experiments and learn what the problems are by seeing it yourself, right? And in my experience, I've also found that this is a sure shot way of finding new problems. Like early in my PhD, I went on this rat hole where I thought there was this kind of complex problem, and my advisor made me run a lot of experiments to understand it before I did anything, right? And in the process, I actually found something else was an interesting problem, like replica selection. And I'm like, hey, that's interesting. And that became half of my thesis afterwards, right? So this is actually a good way to find new problems to begin with. But so one way or the other, when you do the experiments before you build anything, you'll actually get valuable ammunition that will help you frame a good problem, right? So do that. So once you're starting to set up your experiments, make sure that you take the big red button approach to running experiments, right? Have one top level script that takes a commit ID and does everything. And I mean everything. Your script should basically check out your code, build all the artifacts, not just your prototype, but also the baselines. It should set up and refresh the infrastructure, deploy all the binaries, run all the experiments with all the parameter combinations, and make sure to rest the infrastructure between the experiments, collect all the logs, traces, and metadata about all of these runs, and compile all of them into a report where you have all the analysis and the plots, and email you the plot, send the report to a Slack channel, Instagram, whatever, right? Like whatever communication medium you prefer to receive your experiment reports. But the sooner you get to this mode where there's simply no room for manual intervention, the better. Because like I said, the goal is to keep the cycle short and efficient, right? So once you're here, you'll get into this mode where you make some changes to your prototype, you send off this experiment to run, you go get some coffee, you come back and you have a report full of data about how your change affected all your sort of metrics of concern, right? You see all the data in one place. And keep in mind that the tracer bullet methodology applies just as well here as well, right? You're going to be building your experiment infrastructure and your code in tandem with your prototype, right? And in the beginning, you'll start out somewhat simple, and over time, you'll add new baselines, new kinds of configurations, you'll add new types of experiments. as well as new kinds of instrumentation and logging and new types of plots and so on. So this will evolve in tandem with your prototype. So now I'll go into a bit more low-level advice on the nature of the automation itself, right? Some things you should take care of while you're setting up your automation. So the first thing to keep in mind is to record as much experiment metadata as possible. What do I mean? Things like the commit ID that you try to run an experiment with, the timestamps for when the experiments were triggered, the specific parameter combinations that you ran, as well as where you ran the experiment, right? Like what environment did you run it in? Like what were the configuration of the machines you ran it in? What IP addresses did you have? Which machines did you run it in? Record as much of this stuff as possible. And make sure when you record it, you're actually recording it in a machine readable format, something like CSV or JSON or something. And what you really should not do is encode all of this information into like folder names or file names, because that's really fragile. The moment you have to add some kind of new sort of parameter combination, for example, to your experiment, all your parsing code breaks, it's really messy. Just put it in a machine readable format. Now, the reason to do all of this is that it allows you to validate your experiments thoroughly, like at every step of this automation, right? Make sure that you propagate all of this experiment metadata all the way to your graphs. For example, I always make sure that in my graphs, I have the commit ID of the systems that I evaluated, right? And make sure that like at every step, you're basically introducing as many assertions and checks as possible to make sure that your assumptions about what's going on in your experiments are valid. For example, are you sure that the data that you're looking at represents data collected with exactly one commit version of your artifact? Are you sure? Sanity check that. When you configure your workload generators to send like 100 million requests to your database, did your database actually receive 100 million requests? Add a sanity check. Similarly, are you sure there were no failures during your experiment, like no components restarted by accident? Make sure that, like add some checks to be sure that that didn't happen. Ultimately, all of these are factors that can mess up your results and lead you to the wrong conclusion. So don't leave any opportunity for that. Pepper your entire workflow with sanity checks, and collecting a lot of metadata helps you do that. Now, the last bit of advice on the automation side is on making sure that your infrastructure is reproducible. And what this means is you should really never be in a mode where you're setting up all your infrastructure by hand in some sense, right? Like you log into the Amazon EC2 console and you click these pretty buttons to bring up new VMs, and you wait with that, you look at that loading screen that they have, and then when you're done, you stop, right? And similarly, never be in a mode where you're logging into these VMs or switches or machines manually and running commands in a terminal to configure them, right? All of these come in the way of reproducibility. So always script up these above workflows, and there are many reasons to do it. First of all, in conferences which support artifact evaluations, this just means that you already have everything, right? Like you just need to tidy it up a little bit and send it out. For OSDI, for our artifact evaluation, we didn't even spend 2 or 3 hours in doing that, right? We just had to write a bit of documentation, but all the scripts were ready to go. And even if you take a very selfish stance on this, right? I found that often the biggest beneficiary of reproducibility is myself, because stuff happens, right? Like almost every project that I worked on has had had to go through some disaster recovery where, I don't know, my machines failed, my disks died, I lost access to a cluster. And in all of these cases, I had to come up and running in a different infrastructure, and having everything reproducible is a big boon, right? You're not set back, let's say weeks, you're set back maybe a day or two. So do that at least for yourself, but really for the communities as well. So that was all the advice that I had on the experiment side. Now I'll talk a little bit on how to interpret the results that you're getting from your experiments. And the mantra here is always be guided by the measurements and the data that the measurements are producing, right? So one failure mode that I've seen is this tunnel visioning that often happens. And I fall prey to this all the time, where I'm frantically trying to improve performance on some particular benchmark because A, I'm kind of obsessive about these things, but B, like, I don't know, it's just, sometimes it happens, right? You have tunnel vision sometimes. And the way to get out of this rut is to make sure that you always write, let's say, the first few paragraphs of your evaluation section, right? And when you do that, you'll be writing something like, in this paper, our thesis is that X is a good way to do Y, right? And when you actually write it out and spell out what your evaluation goals are, it helps you sort of reprioritize and focus. And I've often found that when I do that exercise, I'm like, okay, wow, I just spent 2 or 3 weeks optimizing something I really shouldn't have wasted time on, right? And the other thing to do is to always stop yourself from going down these rat holes and wait to see a report about all your experiments before you iterate on a change, right? And this also helps you, again, refocus, right? Is this one obscure benchmark really that important relative to the big picture that you're trying to convey, right? Like, it helps you reprioritize. The other sort of behavioral aspect to keep in mind when you're running experiments, interpreting your data, is to make sure that you use your intuition to ask questions, not answer them. This is a quote I'm borrowing from John Ousterhout. Um, and the catch here is that, like, your intuition, like, you should treat your intuition as a hypothesis, not a fact, right? Your intuition is something you develop over time, but it's a noisy signal. So the way this manifests is often when we see a bug or a performance problem, our intuition tells us, I think I know why, right? And the mistake you shouldn't make here is to immediately listen to your intuition, go make the changes, and then continue from there, right? Don't do that. Always augment your workflow or your experiments with additional instrumentation or new kinds of data that you collect, and dig deep into understanding exactly why that bug or performance problem happens before you make changes, right? And you'll often find that your intuition might have been wrong, and you can use this information to, again, recalibrate your intuition. The other way this manifests is in when we see, our system completely thrashing the baselines and end-to-end measurements, and then we celebrate, we open some champagne and say, like, okay, ship it straight to hot crap, we're done here. Don't do that. Don't do that. End-to-end measurements are some of the most misleading numbers that you could possibly look at when you run an experiment, because they have no explanatory power on their own. They never tell you why something is happening, right? So make sure you always augment your end-to-end measurements with the necessary lower level measurements and analysis that will confirm confirm why these numbers look the way they do. And make sure to apply that level of rigor not only to your own prototypes, but also to your baselines, right? Make sure you truly understand why these systems behave the way they do before you believe your end-to-end numbers. So that's all I have. The main message here is, when you have an idea, in order to be effective as a systems researcher, you need to be very good at iterating between building a prototype that exercises your research idea and running experiments to validate them, right? And using the results of that experiments to iterate. And the goal in your process is to gather continuous incremental feedback about your idea. And to do that, we covered some tips. For example, make sure that you always prototype end to end. Test for correctness during prototyping, not while you're running experiments. Making sure that you set up your experiment infrastructure as early as possible. Making sure that you automate your entire experiment workflow so that there's just no room for manual intervention in this process, which lets you be very fast in doing this iteration. And lastly, some advice on how to really look at the measurements when you make decisions on how you want to iterate based on your results. Right? There's a bit more advice that I haven't covered here in the blog post that led to this talk. I encourage you to have a look. But really, most importantly, have fun. You're in a very privileged profession where you get to work on open-ended problems with a lot of autonomy. You get to create things out of thin air, and you get to run these things in the real world and see how it changes the world around you, right? Have fun, enjoy the process. I hope you enjoy systems research as much as I do, and I look forward to your questions. Thank you.